Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Hannah Friedman, who is a PhD student at UC Berkeley. We are happy to have her here today to tell us about optimization over the Grassmannian. Take it away, Hannah.
Hi, thank you so much for coming today. Thank you to the organizers for having me. So today I'm going to tell you about work from two papers, one of which came out last February, called The Two Lives of the Grassmannian, and the other one of which is still very much a work in progress. The common theme will be optimization over the Grassmannian. So before I talk about the Grassmannian, I just want to give a small geometric example to kind of get an idea of how we approach optimization problems from this sort of algebraic point of view. So the problem is this. We have some point in the plane, the real plane, and I want to know which point on the unit circle is closest to this point. So I can write this down as an optimization problem. I want to minimize the distance between my point x and my given point u, subject to the constraint that that x lies on the unit circle, or that x has norm 1. Okay, so how do I solve this? Algebraically, I can write down the Lagrange multiplier system for this problem. I can solve these equations, and I get that, you know, to find x, I scale u to be on the unit circle, and then I can make u either positive or negative. And we can also look at the picture of this. So we see that there are 2 points that solve this problem, this Lagrange multiplier problem. And we see that one of them is actually the minimum, the one that's closer to u, and the other one is the maximum. So the setup of the problem is that we're given some function that we want to minimize or maximize. We're given some variety, which are the constraints that we want to maximize over. And the output of this method is that we get some set of critical points that will include the optimal solution, but not all of the critical points are even like local minima or maxima. So just to briefly refresh what this, how this Lagrange multiplier thing works. So in general, if we have some function x that we want to minimize or maximize, and we have some constraints, g, we can write down this function of x and some parameters lambda called the Lagrangian. And we say that x is a critical point if the gradient of the Lagrangian is 0. So in other words, if x lies on the variety, or x satisfies the constraints, this is a requirement, and also that the gradient of f is in the span of the gradients of the constraints g. Okay, so adding in these extra variables can be a bit like problematic, because if we want to think about this from like an algebraic point of view, maybe we're in a ring, and now when we add in the extra variables lambda, we have to go to like a bigger ring. And so this can get computationally a bit difficult. There's another way that we can formulate this to avoid adding in these extra variables. And to do that, we can enforce the condition that the gradient of f is in the column span of the Jacobian of g. And we do that by saying that if I augment the Jacobian of g by adding in the gradient of f, and I take the rank, this is the same as just the rank of the Jacobian of g. And then we still need the condition that x satisfies the constraints of g. And here we're using the convention that the columns of the Jacobian are indexed by the functions and the rows are indexed by variables. Okay, so to solve our optimization problem, what we do is we're given some function f that we want to optimize. We're given some polynomial constraints, g of x in this case. And we want to find all of the points x that satisfy these equations. So first, that the rank of this Jacobian with the augmented with the gradient of f is the same as the rank of the Jacobian without the added gradient, and that x lies on the variety. Okay, so we go from optimization problem to critical points. And it turns out that in a lot of situations, this set turns out to be zero-dimensional, or a finite set of points. And when that's the case, we call this number of points the algebraic degree of the optimization problem. When it's not the case, if it's some positive dimensional variety, we can still think about the degree. And just a reminder of what that means, sort of like a generalization of how many points there are in the variety. So we can take our one-dimensional space here in the bottom left corner, there's a cubic, and we intersect it with a linear subspace of complementary dimension, in this case, a line. And we see that there are 3 intersection points, finitely many intersection points, and we call this the degree of the variety. And in the case that the set is positive dimensional, we can still look at like the degree of this variety. We don't call it the algebraic degree of the problem, but it can still give us some idea of how hard the problem is, which I want to talk about now. So why might we care about the algebraic degree of the problem? It sort of gives a measure of how difficult the problem is to solve if you want the absolutely correct answer. If you want to be really, really confident that you got the true maximum, you have to compute all these critical points and then test them to see which of them is the maximum. And so the algebraic degree gives you sort of a measure of difficulty for doing that. Okay, so there are a bunch of like classes of optimization problems that people study in algebraic statistics. So the first one we already saw. This is where we pick a point and we minimize or maximize the distance from our variety, from a point on our variety to that special point that we picked u. And the number of critical points of this is called the Euclidean distance degree. So this is something that we can associate to a variety. So if you let f be this function fu on the left, and we pick a variety G, we can compute the critical points of this optimization problem, and the answer will be called the Euclidean distance degree of the variety G. And then there's this interesting phenomenon where these statistical degrees, or these degrees that come from optimization problems, turn out to be actually like have relationships with sort of more with quantities about coming from the variety that come more from pure math. So in this case, there's this thing called polar degrees, which give you a lot of information about a variety. And if the variety is nice enough, this doesn't always happen, then the Euclidean distance degree is equal to the sum of the polar degrees. Okay, so another example that's maybe more statistics oriented is called the maximum likelihood degree. So here, the setup is that we take f to be the log likelihood function. And the idea here is that u is some data we've collected. So that means it's some vector that says we've observed the state I, ui number of times. And if we think that the probability distribution that governs this experiment that we're doing maybe satisfy some constraints, we can optimize this likelihood, or maximize this log likelihood function to find the probabilities xi that best explain the data ui. And this is called a maximum likelihood estimator. So again, if f of x is this maximum likelihood, or this log likelihood function, we optimize, we can get the maximum likelihood or ML degree of a variety. And again, if the variety is nice enough, this is equal to the signed Euler characteristic of the variety. Okay, and then the last example is called linear optimization degree. And here we're just taking some linear form, some generic linear form, and minimizing or maximizing it over the variety. And again, when the variety is nice enough, then this is equal to the first polar degree of the variety. So throughout the talk, I want to give you an example of each of these problems. So the first one we already did, and the next two will be more Grassmannian related, which maybe we should talk about because I've been talking for a little bit now and the Grassmannian hasn't even come up yet. So just as a reminder, the Grassmannian is the space of k-dimensional subspaces of an n space. There are a bunch of different ways to work with the Grassmannian as a variety. So one way to think about it is we want to write down we want a way to represent some k-dimensional subspace of n space. We can take bases, just take k linearly independent vectors and mod out by the equivalence relation that if they generate the same space, then they're equivalent. Okay, so this is one way of working with the Grassmannian. This will come up a little bit later in the talk, but is maybe not like the easiest way to work with because we have these equivalence classes that are a bit, maybe a bit fiddly. Okay, so another option is called the Pluecker embedding, where you use Pluecker coordinates. I'll talk about that on the next slide. And then the third option is orthogonal projection matrices. And I'll also talk about that more like right now. So Pluecker coordinates and orthogonal projection matrices, these are the two lives of the Grassmannian that this paper is about that came out in February. So these are both like very well studied embeddings of the Grassmannian, but they are very different. So the Pluecker coordinates come up more in like pure math and algebraic geometry. They embed the Grassmannian as a projective variety, and they have like really, really nice combinatorial structure. The orthogonal projection matrices come up more in applied settings, and they embed the Grassmannian as an affine variety. So these are like feel very different, but are really representing the same thing. And so maybe there's a way that they should be able to talk to each other. And yeah, I will talk about that after I say a bit more about what each of these are. So how do the Pluecker coordinates work? Well, let's say I have some k-dimensional subspace of Rn, and I want to represent it with some Pluecker coordinates. And let's say I have some matrix whose columns span my subspace. So what I do is I write down my matrix, I take all of the maximal minors of the matrix, and these we'll call these, xi, where I is the subset of rows that we pick to form the submatrix that we take the determinant of. And these will be, these don't depend on the choice of A as long as the columns span the same space. And these are called the Pluecker coordinates. So for example, if we have this matrix A, we can just take all the 2x2 minors of this matrix. We call these the xij's. And we can do, for example, like an elimination computation to get this, where so we can plug all of these equations into a computer and say, eliminate all the A's. And this leaves us with a bunch of relations between the xij's. These are called the Pluecker relations. And when K is 2, these are the 4x4 Pfaffians of a skew symmetric matrix. And yeah, as I mentioned before, there's also a lot of like really nice combinatorics that comes with the Pluecker coordinates. Okay, So the second life, these orthogonal projection matrices, again, same setup. We have some subspace we want to represent, and we have a basis. What we can do here is just take the projection matrix on the orthogonal projection matrix onto the basis. Sorry, onto the subspace. So this is a projection, orthogonal projection matrix that has some nice properties. So it's symmetric, it's equal to its own square, and it has trace k, which is equivalent to having rank k in this case. And it turns out that these are actually enough. So any matrix like satisfying these properties is a projection matrix onto a k-dimensional subspace of Rn. And actually we can do even better and say that this ideal actually is the ideal for this variety. So this variety is irreducible, and this ideal is prime, or this is actually like the ideal of this projection Grassmannian. We'll call this orthogonal projection matrix embedding. We'll call this the projection Grassmannian, and we'll denote it with PGRKN here. Okay, so I mentioned that these Pluecker relations and orthogonal projection matrices talk to each other. And the details of this are not so important, but I just wanted to have mentioned it, that you can go back and forth. So to go from a projection matrix to Pluecker coordinates, you just take any, the D should be a K here. You take any K linearly independent rows, and you take the minors of these. And then to go back, you use this formula. Okay. So next I want to talk about a maximum likelihood estimation problem on the Grassmannian. So here we will look at the Pluecker embedding. Yeah, so this is the same formula that I had before. In this case, the state space is size k subsets of the numbers 1 up to n. And again, the situation is like we've sampled from this subspace, we've observed the set I, ui times, and we think that the probabilities kind of come from being from these like maximal minors of some matrix. And we want to know which point on the Grassmannian would best explain this data U. So we can compute these maximum likelihood degrees using a software that I'll talk a bit more about later. And we get these like nice numbers. This is just the k equals 2 case. So this grows like very, very quickly. Right? By n equals 8, we're already up to 5 digits here in the maximum likelihood degrees. So this is like quite a complicated model. Okay. So there's another thing that we can do that maybe seems a bit unmotivated at first, but hopefully I will be able to motivate this for you. So one thing with probability and with algebraic statistics, really, algebra works very, very nicely over the complex numbers. In probability, what we really kind of want with our probability distributions is for them to not only be real, but also maybe we want them to be like non-negative. So one thing that's sort of natural to look at then is this thing called the squared Grassmannian. And we get this from just squaring each coordinate in the vector of Pluecker coordinates. And we take, this is some like squaring map, and we take the image, we call this the squared Grassmannian, and we do the same like maximum likelihood optimization problem on this variety. And we can do the same thing. We compute the ML degrees, and we get that they're actually a bit lower than the ML degrees for the regular Grassmannian. And this is kind of surprising because this squared Grassmannian is a more complicated variety. Like you can see that, I mean, it's from squaring the coordinates. It means the ideal that cuts it out is generated by higher degree polynomials. So it's a bit like we kind of would expect that maybe the maximum likelihood degrees would be higher. And the fact that they're not points to the idea that maybe there's like some hidden probability thing going on here. And it turns out this is actually true. So to like kind of understand how this works, I will first tell you what a determinantal point process is. So this problem on the right is an example of a determinantal point process. And in general, yeah, this is kind of a lot of words, but basically a determinantal point process is governed by some matrix P. P is some n by n matrix. And the probability of a subset being contained in this, in our random variable, is, oh, sorry, okay, there's a mistake on the slide. So this should be not the size k subsets of n, but all subsets of n of any size. Okay, so the probability of a set I being contained in our random subset that we pick is equal to the principal minor of our kernel matrix whose rows and columns are indexed by that set. So for example, if we have a 3 by 3 matrix, this is our P, it's symmetric, and hopefully has eigenvalues in 0, 1, so that this actually kind of makes sense as a probability distribution. So the probability that 2 is contained in some subset that we pick is given by the 1 by 1 minor, P2, 2. And the probability that 1 and 3 are in the subset is given by the 1, 3 minor, which is a 2 by 2, excuse me, 2 by 2 minor. And these determinantal point processes are very nice. They're very good at modeling like sort of repulsive behavior between the elements in the subset. They were first introduced in physics to study fermions and now are often used in machine learning. And it turns out that this something very nice happens when our matrix P happens to be in the projection Grassmannian. So when P is on the projection Grassmannian, then these probabilities turn out to actually be proportional to these squared Pluecker coordinates. And this relationship, I won't talk about this in detail, but this comes from the relationship between the Pluecker embedding and the projection matrix embedding that I mentioned earlier. And so the consequence of this is basically that this maximum likelihood estimation problem over the squared Grassmannian is actually a determinantal point process when the kernel is in the projection Grassmannian for k and n. Okay, so I think this was like maybe the most difficult part of the talk. From now on, we're just going to talk about the projection Grassmannian, and I want to tell you about the linear optimization degree of the projection Grassmannian. But maybe now is a good point to like pause briefly and ask if there are any questions. Go ahead.
Yeah, could you go back to, I think it was 2 slides ago. Yeah, so I'm looking at these maximum likelihood degrees. It looks like that sequence is growing like a factorial, whereas on the left-hand side, I don't know, I'm guessing it's just kind of multiplying by about 10 every time. What happens if you go kind of asymptotically? Is it true that the ones on the right are growing slower than the left?
Yeah, that's a great question. I don't know. So this is pretty much the limit to which we can compute Yeah, the ones on the right are definitely growing factorially, and I'm not sure. So yeah, it's possible that maybe this is just sort of a small n situation that's happening here. But also, yes, there's also like behavior for larger k that, yeah, that I think also exhibits this pattern, if I remember correctly. Yeah.
Yeah. Okay, thank you.
Yeah. Okay. So the linear optimization degree story is a bit less direct. So we actually will go back to basics and start with the eigenvalue problem. So let's say we have some matrix and we want to find the k most significant eigenvectors of this matrix. We can solve this by an optimization problem that looks like this. And I'll just say a word about the constraints here. These are like quite important to have because if we didn't have, so what this is saying is that the columns of X are orthogonal to one another. If we didn't have that, then, you know, we could just get the most significant eigenvector k times. And then we also scale because if we didn't scale, we would get, you know, a whole family of eigenvectors. So we actually want each vector to have norm 1. That's sort of where those conditions come from. So for this eigenvalue problem, because we kind of know the optimal solution a priori, we can kind of guess at what the critical points are. And so we're actually going to compute the critical points instead of just computing the number of critical points. So here again is the problem on the left. And again, this is equivalent to the inner product of two vectors being 1 if they're the same and 0 if they're not. And just as a reminder, we're trying to compute all the points x that satisfy this rank condition on the Jacobian and also that lie on the variety. So in this case, we really want, you know, x transpose x to be the identity. And we also want the gradient of our objective function, in this case, the trace, to be in the column span of the Jacobian. And I left lots of room here so we can actually write out what these are. So the gradient of the trace can just be worked out. We get something that looks like this. And we compute the Jacobian, we get this. And again, here we're using the convention that each column corresponds to one of the constraint equations, and each row is a variable, except in this case, these are vectors. So we're not seeing the actual rows in this depiction here. So this first like diagonal matrix on the left is comes from all of the constraints that x, the inner product of xi with itself should be 1. And then this rectangle on the right is all of the orthogonality relations between two different xi's and xj's. And we can see right away that if all of the xi's are eigenvectors of M, then the gradient of the trace is definitely in the in this column span of this matrix, because we really actually only just need the first square, because when we do mxi, it gets scaled by lambda I, and we can add up all the columns, scaling them with lambdas. Okay, so we're happy. So it turns out you can, not only can you pick like the most significant eigenvectors and get a critical point, you can pick any set of eigenvectors in any order and get a critical point. And one question we might ask now is, did we get all of the critical points? And the answer is no. And the reason for that is that when we optimize in this way, we're not really optimizing over the eigenvectors, we're optimizing over the spaces that they span. So one way to see why this is true is, okay, there are a bunch of like orthonormal bases for this plane that I just put on the slide here, and we can get between them by an action of the orthogonal group. So you can take any k by k matrix, multiply x by this matrix, and if we then plug that matrix x theta into the objective function, it remains unchanged. And the same thing is true for the constraint. So will be also satisfied as long as x transpose x is satisfied. So what this means is that we can take any critical point that we have and multiply by theta and get another critical point, where theta is anything in the orthogonal group. And it turns out that this is actually all of the critical points that we have. So if we want to look at this variety of critical points, what we get is n choose k varieties that are isomorphic to the orthogonal group. So the dimension is the same as the dimension of the orthogonal group, and the degree is n choose k times the degree of the orthogonal group, because we have n choose k copies. So for example, when k is 2, we have a bunch of copies of the orthogonal group, and each copy has degree 4. So the variety has degree 4 times n choose 2. Okay. So this is like maybe not ideal. It's kind of nice when we have actually like a finite set of critical points, we can talk about the algebraic degree of the problem. And really, like, we want to, if we're optimizing over like subspaces anyway, rather than basis vectors, maybe we want to use like a coordinate-free representation. And it turns out that this is actually like quite advantageous too from a numerical point of view. And this is a figure from a paper called Simpler Grassmannian Optimization. And on the left, we can see the performance of a bunch of algorithms for using the model that I just talked to you about. And on the right is the same thing, but for a model that's very similar to the orthogonal projection matrices. It's not quite the same, but it's very similar. And it turns out that numerically, this coordinate-free representation is more stable than the method that I just showed you. Okay, so just to like quickly refresh, this is what we're working with here. So we can assume our matrix is symmetric, and then the equations we have are that the matrix is equal to its square and that it has trace k, and this defines the projection Grassmannian. So we can note that if the columns of x are already orthonormal, then this little inner part of the formula vanishes, and we get that P is just XX transpose. And we can kind of find this XX transpose if we use this cyclic property of the trace. And then, okay, it's a bit more subtle than this, but basically we can just replace XX transpose with P and replace the condition on X with this condition that P is in the projection Grassmannian. And we've now sort of transformed our coordinatized optimization problem to a coordinate-free optimization problem. And what this does is that, so you can see that if I multiply x on the right by theta, then P is unchanged. So what this means is that those orthogonal groups that we had before, they all get smushed down into a single point. And so, okay, again, this is not a proof, but the result is that we actually do get finitely many critical points when we formulate the eigenvalue problem over the projection Grassmannian. And the way that we do this is that we can pick any size k subset of our n eigenvectors, and we form this matrix in the middle here. And so there's n choose k points that we get from this. And this is like 1 point for each copy of the orthogonal group. in the previous formulation of the problem. Okay, so there's like one other thing that I want to note about this problem, which is that the trace of MP is actually linear in the entries of P. And this is very exciting because I promised you that this would be about the linear optimization degree of the projection Grassmannian. And in fact, this is the same thing as the linear optimization degree of the projection Grassmannian. So if you don't believe me, we can go back and forth between this trace and we can pick some like generic coordinates uij. And we can go back and forth. This is like a pretty harmless transformation, just multiplying by 2, which means that if the u's are generic, the m's are generic, and vice versa. And so we basically have that this trace of MP is a generic linear form over the projection Grassmannian. And so the consequence of this is that the degree of the eigenvalue problem over the projection Grassmannian is equal to the linear optimization degree of the projection Grassmannian. And both of these are equal to n choose k. So what I think is really cool about this is that we're able to take this eigenvalue problem that's like quite well understood. We already have some intuition for like what the critical points might be. And this allows us to compute this like linear optimization degree of the projection Grassmannian because they're just exactly the same. And so the question is like, well, if we can do this for the Grassmannian, maybe it would be cool if we could do this for flag varieties too. So just a quick refresher, for flag varieties, we take basically a bunch of nested subspaces, and we'll just think about complete flags for today. So we'll take a subspace with just the origin of dimension 0, and then a line, and then a plane. In this example, for instance, don't go up very high. And yeah, so we can think about this as like a generalization of the Grassmannian. And there are projection coordinates for the flag variety too. So down here we have, these are sort of very similar equations to the ones that cut out the projection Grassmannian, although here I'm already assuming that they're symmetric. Each PI is symmetric. So, okay, so these second two equate the two rightmost equations, trace of PI is I. This is familiar. This is saying that the rank of PI is I. And then PI squared is I. Okay, this says it's a projection matrix. And then the first equation, PI plus 1, PI equals PI. This is saying that the spaces are nested. So if I project onto the ith subspace and then I project onto the ith plus first subspace, I should just get the same thing that I had before. Okay, so we kind of want to like write down the same nice equalities for the flag variety that we had for the Grassmannian. And we can do this on the left. There's a problem called the heterogeneous quadrics minimization problem. And I will tell you more about that in a second. On the right we're a bit stumped. This is kind of hard. And yeah, more on that in a minute too. So the heterogeneous quadrics minimization problem is basically that instead of picking one M, we pick a bunch of M's. And if we think about it in this old formulation with the X's, we can think about each column vector of X getting its own M. And so it turns out if we set all the MIs equal to one another, then we just get back the original eigenvalue problem. So that's where the heterogeneous kind of comes from. So we're taking one M and then replacing it with a bunch of M's. Okay, so again, we can formulate this as a problem over this projection flag, or these projection flag coordinates. And it's worth noting that these MIs are not the same. So to go between these, you have to like take some differences, but it's doable. And then you can formulate this problem in either way that you prefer. And then we can start computing. So in this case, we kind of don't have such a good guess of like what the critical points are going to be. So first step is get a computer and start producing numbers. So I like to use this software called homotopy continuation, which is a Julia package. It's very user-friendly, I think, and very easy to get started with, but it's basically numerical algebraic geometry techniques for solving polynomial equations, which is what these minors and constraints turn out to be. Okay, so we can do this for small n and k. This gets unwieldy very quickly. We have a guess for k equals 2 of what this formula might be. And k equals 3, who knows? So if you recognize these numbers, please let me know. And yeah, again, this is just for this this case or this problem on the left. This is not even for the projection Grassmannian. So the projection Grassmannian is a bit difficult to work with the software because you actually get like many variables, many equations. There's a lot to do. And so the hope was to sort of start with this problem, get some intuition for what we expect the x's to be, and then maybe try to bring this to the projection Grassmannian case. But this is already turning out to be quite difficult. So TBD on whether we will actually find out the linear optimization degree of the flag variety. Oh yeah, I forgot to mention that. So you can kind of do the same transformation here, and it turns out that that this problem on the right is the same as the linear optimization degree of the flag variety. And it's exactly the same trick as I showed you before. Pretty straightforward. Okay, so before I finish, I just wanted to mention, so we sort of saw examples of all of these different like kinds of degree problems. We looked at like a baby example of Euclidean distance degree. We talked about maximum likelihood degree on the Grassmannian and its Pluecker embedding. And we talked about the linear optimization degree of the projection Grassmannian and its connection to the eigenvalue problem. And there's lots more related to this if you're interested. Okay, yeah, so before I go, I just want to mention a couple references. So on the left, I have lists of some papers where these different degrees were first introduced. And okay, maybe linear optimization degree is a bit more recent, but the other ones, there's like a lot of work that's already been done on these. And then on the right is some references for like optimization on the Grassmannian and on flag varieties. So thank you so much for coming and listening.
All right, let's smash that reaction button. And are there any questions or comments?